Example 3.1. A 1 kilogram ball is at rest on a floor in a 2 by 2 by 2 cubic meter room of air at standard temperature and pressure. A. What is the thermal energy of the air in the room? What fraction of thermal energy would have to be converted to the ball for it to spontaneously launch to a height of 1 meter? C. By how much would the air temperature have to decrease to launch the ball? Your answer to C is so small as to be unnoticeable, yet this event never happens. Why not? A. Treating air as a diatomic gas, ideal gas that is, that means it has to have a low density. That immediately tells us that then CV has to be 5/2 R. So the internal energy of the air has to be the number of air molecules times 5/2 kBT. So that means here is that I have to calculate the number of gas particles first. So I'm going to use the ideal gas law to calculate N of air. Now the way I'll do this here is that I'll use the per molecule ideal gas law, which then says this, that PV is then going to be N of air times kBT, which then immediately tells us that if I now solve for the number of gas molecules, that this will be PV divided by kBT. And this is all happening at standard temperature and pressure. So let's do this here. And the other thing here is that note that the volume is going to be 2 by 2 by 2 meters cubed, which is of course 8 meters cubed. So now if I just substitute everything in, I'm really looking at a box or a room that looks something like this. So if I look at my box, this is telling me here that this is at standard pressure and temperature, and that each of these dimensions is 2 meters. And then, of course, that dimension right there is 2 meters. So just to visualize this thing. So then, using the ideal gas, then this tells me here is that now I'm going to come in and I'm going to say, so using proper units, this is 10 to the minus 5, 10 to the positive 5 pascals. My volume is going to be 8 meters cubed. And then I have to divide by the Boltzmann constant. And then finally, standard temperature, which is 293 K. So if I compute that number, I get 2.15 times 10 to the 26 air particles, which is, of course, N2 and O2 combinations. So now I have the number of air molecules in this room. So now I can use the internal energy. So the internal energy is then going to be I internal, and then this is going to be N of the air times 5/2 kBT. Now, I could have done this with a lot of cancellations. Like one example, if I just replace, and I didn't do that calculation for the number of particles, I could have just come in here and I could have done this instead. So then I'm going to have kBT times 5/2 kBT. And you're going to see here is that there's a lot of cancellations here. You can see that cancels us with that. And you get this relationship. The reason why I didn't do this is that I'm going to need the number of particles later on. But under normal conditions, I would have done this immediately. So if I just stick to this form here, then I know that the pressure, and then here I have my volume, and this will give me units of joules, so I get 2.02 times 10 to the 6 joules for the internal energy of the room. Okay, so once again, the reason why I didn't do it is because I'm going to need the number of particles later on. So now, here's what we find. We're on B. And what we're trying to do is that we want to see, so to launch a ball, up to a height of 1 meter, it requires a minimum potential energy of this. So you have to change the gravitational potential, which then of course is mg delta y. So if I start to look at this, I have a mass of 1 kilogram. Of course, there's the acceleration due to gravity, and then it goes up 1 meter. So this clearly gives me 9.81 joules, but because this is so small compared to everything else, I'm just going to come in here and I'm going to say that this is 10 joules. So right now, this is how much energy is required for a ball to go 1 meter. So now the question is, let me move this higher. If one could extract this energy from the room's internal energy, in the air, what percentage would this be of the internal energy of the air? So when you look at this thing, well, this is just a fairly simple calculation because this is really what we're talking about. So you're trying to take 10 joules out of the room, which is of the order of megajoules, right? So if you look at this thing here, you could see that this number, if we were to do it, it's going to be really what? 9.81 joules divided into 2.02 times 10 to the 6. Well, we can just approximate that, right? Because the numbers are so gigantic that this would be 10 over 20 times 10 to the 5. So you could see here is that this will be 5 times 10 to the minus 4. So, I mean, if we write this number out, it is a tiny percentage. In other words, this would be, so if I multiply this by 100, let me make sure I got this right. I'm going to go, this would then be 0.05%, which would then be the percentage of energy that you would have to take from the air in the room. Clearly, this is a very tiny number, right? This is infinitesimal. We want to say that, right? That's an infinitesimal amount. So now we get to C here. And what we said in C here is by how much would the air temperature change? Right, so now the question is by how much does the air temperature change with this transfer of energy? Well, if this amount of energy is infinitesimal, then clearly it has to be infinitesimal as well. So then I could say that the decrease in internal energy, but the internal energy is connected to the temperature, is, of course, infinitesimal. Now, if we try to compute this, so to compute this temperature difference, or this temperature change, one must use derivatives because we are dealing with tiny numbers. So what I'm going to do now is that I'm going to transition to derivatives here. So if I transition to derivatives, I say that I have some internal energy in the room. And then what I'm going to see here is that there is a tiny change in internal energy. So what this tells me here is that because the internal energy is proportional to the temperature, we then say that this infinitesimal change in the internal energy is also an infinitesimal change in the temperature. Now, how does that dt come in? So what this really tells us is that, maybe I should write it over here. The decrease in temperature is given by this here, right? It's got to be T2, and then this is the original temperature at room temperature, 293 K, and then I'm going to subtract this tiny amount. Okay, I got to subtract that tiny amount. So this implies here is that we are looking for this dt. Okay, so that means here I must use the total derivative to get this. And what I mean by that is that the total derivative of any function using a chain rule type argument says that the derivative of the temperature, this partial derivative, times the total derivative of the internal energy, right? And then we can, when we look at this thing, here's what we see. This guy right here, this is the infinitesimal change in internal energy. But we know what that is, right? We know what that is because the fractional change of the internal energy must be what it lost to gravitational potential. So in this case, it's minus 10 joules, right? So this is telling me how much was transferred to the ball. So now I have to deal with this expression here. So here we go. So now what I'm going to do here is that I got to deal with that partial derivative. So this guy is what we must calculate. But we know how to do that. So this partial derivative is this. Well, if I'm going to take the partial derivative of that, this is just the inverse of this, but I know what the internal energy is, right? We know that the internal energy is 5/2 N of air kBT. And clearly, when I take the derivative of this, this is the same as 5/2 N air kBT. So now I can substitute this into our infinitesimal change in the temperature. So subbing this into our dt relation, we then see that dt, which is this guy, and then we have this infinitesimal change in the internal energy. Well, that's just the inverse of this. So this has to be given by what? 5N of air kB times 2, and that has to be, so now I can put in my numbers. So if I put in my numbers, look what I'm seeing here. I'm seeing that we know that I'm going to get what? I'm going to get 5, and then the number of particles, which is what we already calculated up above, and then this times the Boltzmann constant, and then this guy is going to be 2 times the amount of energy. And so when you compute this number, we get a value that reads minus 0.0013 Kelvin. And you could see that this is an infinitesimal decrease in temperature. Well, you know what? That's not the way we defined it, so I'm going to keep that with the plus sign. Right? We know that it's a decrease, so then the fractional change in the decrease in temperature is then going to be dt over t. That's got to be 0.0013 divided by the room temperature. And you could see that this is now 10 to the minus 6 for the fractional. But if I want the percentage, that has to be 0.0003%, which is now this guy right here. That's the percentage, which is, of course, tiny.